Hi, welcome to Solution Calculations Part 2, percent by mass and parts per million. Percent by mass and parts per million are both based on masses rather than moles. So in some areas of study or into some populations, this can be a little bit more useful if the mole is, less commonly understood. A lot of times environmental studies tend to use these units because they're a little bit easier to communicate to the general public. Your percent by mass formula is on table T. I did kind of modify or translate it a little bit the way that I have it written on the board. So this is a part over whole, your part being your solute and your whole being your solution. It's actually going to be very important, and I'm going to show you why in this next calculation. So if we want to know the percent by mass of sodium hydroxide in a solution, if we have 2.5 grams of our solute added to 50 milliliters of water. Now, for our purposes, remember 50 milliliters of water is pretty close to 50 grams. The density of water is 1 gram per milliliter. We can assume this is close enough to 20 degrees Celsius where that works. So to calculate our percent, we're going to do our grams of solute, which is 2.50. Now we need our actual grams of solution on the bottom. If we mix these two masses together, we actually have 52.50 grams as a mass of our whole solution. So we added the 50 grams of water to the amount of NaOH that we put in. Which gives us a grand total of 4.76%. So percent by mass is pretty similar to other percent calculations we've done. Parts per million is another way of expressing concentration, and parts per million works for things that you're going to have a much smaller concentration of, but maybe you don't want to have to express the number as a decimal. So the first part of this, you'll notice, is still a part over whole, grams of solute over liters of solution calculation. So we actually are going to do basically the same question, only make it come out in parts per million. So now we're going to know concentration in parts per million when we have 2.5 grams of NaOH added to 50 milliliters or 50 grams of water. So we still have 2.50 grams on top and 52.50 grams on the bottom. Only this time we're going to multiply by a million. So we're pretending we have a million parts instead of just 100 like in percent. If you actually don't sum your numbers on the bottom for this, you will still get you'll probably still get the correct answer, because usually, since you're multiplying this by a million, it kind of washes that out, but it's good to be in the habit of putting the total mass of solution on the bottom. So this comes out to 47,619 parts per million, which could be rounded to 50,000 parts per million. These are pretty large numbers, usually with parts per million, or another similar unit, parts per billion. We're talking about very small amounts of things. So parts per billion, a lot of times they'll talk about contaminants like mercury or lead in water, and they'll talk about that in terms of parts per million or billion. So another calculation we can try. If we have approximately 0.0043 grams of oxygen dissolved in 100 milliliters of water, what is the concentration in parts per million? So 0.0043 grams. This is a great example of one where if you just put 100 on the bottom, you're going to get a very, very similar answer. You're going to get the correct answer. I like to put the 0043 because I feel like it makes it more part of whole. It's a little bit more correct. But with your rounding error, once you multiply by a million, it'll come out fine, whichever way you do it. So this is a more adequate example in terms of we have a very small amount of oxygen. It's just 0.0043 grams, but it makes it look like a number that people can kind of handle a little bit better because it's not a decimal. So it's 43 parts per million. So here's some various calculations to try. These include parts per million, and they also include molarity. Pause the video, give each of these a try, and I'll put the work up in just a moment. So here are your answers for each of these. I've shown the work. The first one, I showed the work for both the percent and parts per million. Second one, you had to do a mole calculation first. Remember that your 500 milliliters is actually 0.5 liters. You have to bloop, bloop, bloop that. The next one was a dilution calculation, so M1V1 equals M2V2. And finally, the last one, you actually have to start with molarity. Remember, your 300 mils is 0.3 liters, and then you had to end that one up with a mole calculation, 0.6 moles times your 94 grams. And that wraps up concentration.